like if you're a photon is traveling at the speed of light. So when you're traveling at the speed of light, and you're a photon, then that means that the photon sees the whole universe at once, pretty much. Like if you're at the event horizon, the edge of the black hole, where somebody could just get trapped there and they could see the end of the universe, right? Just like how a photon kind of sees everything at once. If you were riding on a photon, like if you were riding it like a horse, because remember, as you approach the speed of light, time slows down. You know what I'm saying? Time slows down as you approach the speed of light. So once you hit the speed of light, then time stops, and then we get into light years and things like that, but everything else around you is going to, if you're traveling light years, everybody else is aging way faster than you're aging, So it's like, that's why if you want to talk about Feynman diagrams, look up Richard Feynman, Feynman, Richard Feynman. He's a very famous physicist, and he came up with a lot of these charts that showed you could look at it as predestination or going outside other dimensions, but he would show that if a proton, hence an antiproton, and they hit each other, they're going to explode and turn into light. They're going to turn into a photon, right? Or you could look at it as in the reverse, the photon exploded and the photon split into a positron and an electron, right? The opposite of the electron is a positron. So if a positron and an electron hit, that's going to create the photon, right? All right, we're back. Yeah, so I'm going to finish up this lecture on, I was just talking about Richard Feynman and antiparticles. And I'm going to show you how that relates to just different dimensions. Okay, so what Richard Feynman was able to tell us is that he found out that, if you have an antiparticle, let's say you take a proton, the antiparticle would be an antiproton, right? You got a proton and an antiproton. So let's say you take an electron and a positron, that's the opposites. The electron is one particle and the positron is the antiparticle. The electron will hit the positron and they'll collide, and and that forms a photon will shoot off of that, right? So photons, like I was saying, are kind of outside of our fourth dimension time because they're going at the speed of light, right? So they're kind of existing more so in other dimensions. Whereas us, even though we're only aware of the third and fourth dimension, we're still existing in higher dimensions. And like I was saying about the vectors, axis vectors, every dimension is just another axis, right? So one dimension is just, zero dimensions is just a point, right? One dimension is just a line, right? Two dimensions are two lines. So that's X and Y, like an XY graph, right? Then we got X, Y, Z. That's three dimensions, right? Then X, Y, Z, and let's say you add F in there, that's four dimensions. And let's say X, Y, Z, F, and then I'm going to say G, and that'll be the fifth dimension. You can just keep adding them on. And, a lot of people, they stop at 11 generally these days, most scientists. But, there's a lot of debates on how many dimensions there are. And every dimension isn't the same. The properties of some dimensions are different, right? But the thing is that, obviously we're existing in different dimensions, and you're telling people that if there was a Disney movie back in the day where this kid flew in this spaceship picked him up in the woods, and he flew in the spaceship, and, he was gone for like 7 years from his parents' perspective, but from his perspective, he just, was flying on the spaceship for a night. And, so I'm sure a lot of y'all have seen that Disney movie. But that's just an example of relativity and how that works, And we're also going to talk about, multiverses too. And, because this, as we were just talking about dimensionality earlier, we're going to relate that to the Feynman diagrams. So the Feynman diagrams present a map. They present a map of the movement of particles, right? So particles collide, particles create new particles. Our bodies are really actually pretty much light encapsulated in different types of magnetism. You know what I'm saying? There's electromagnetism, there's, strong force, weak force, we can go through all these different forces, even the black body force, a newer force, the black body force, right? And we got gravity, force, so, as different particles can be viewed as a wave or a particle, that same thing, that same principle holds true in, when you're talking about things being outside of the third dimension or things like that, because if you're talking about the third dimension, as we've covered before, the third dimension is 3 axis points, X, Y, and Z. And the fourth dimension is adding a new access point, right? And that's time. But yeah, so the Feynman diagrams present maps, right? A map that is outside of normal time, just like how this animation that I'm in right now is kind of overlapping and zooming out into these different, a loop of these different worlds, a couple of different worlds, right? So, as we have an electron and we have a positron, the electron can be represented by E, and you see that there's a line called a ray, right? We call that a ray, right? A ray is a line that has an arrow. So E will have a arrow going a certain direction. So that's an electron moving in a certain direction. And the opposite of an electron is a positron, and the positron is going to be moving in the opposite direction. It's going backwards in time, right? So an electron's moving forwards in time, and a positron's moving backwards in time. And it's also important to note that 10%, more within the Bohr model, 10% of the electrons in our body can be anywhere in the universe at any one time. And earlier, I'd also like to point out, I failed to mention quantum entanglement. Quantum entanglement is the science of me being able to connect with my father, because it's like originally I came from him in a farther back in the trail of the fourth dimension, because if you look at the fourth dimension as what you do in a day, like let's say you just look in the mirror and it's just 1 second, then that's basically showing you at that instant. But then if you do like take a time-lapse photo, like when you see cars driving through the city and you see the lights as strings, your life looks more like a worm. Like you're going to work, you're going to the grocery store, you're going to these places. It's more of like a trail of your body, And I first learned about the fourth dimension under Steve Segur at the Paideia School when I was in high school in Atlanta. And, rest in peace, Steve Segur. And, he was working with people at Brown University. And I guess he went to Brown University. But, yeah, he was working with a lot of students in the 90s. And so in high school, he was telling us about the fourth dimension. We were just kind of bugged out like, oh wow, like it's, But really, the fourth dimension is not very difficult to understand, because really it's just time relative to our 3D world. So every higher dimension up, the fifth dimension is time relative to people in the fourth dimension. But people that are living in a fourth dimensional plane and not just a 3D plane, they, they're looking at the world in a time-lapse view. And that's similar to what Feynman diagrams are. Feynman diagrams are stepping outside of normal time and showing a bigger picture of kind of like almost like a predestination type of a thing where there's a bunch of particle events happening. It looks like a star chart. I'll show the graphs or these diagrams. They look like star charts, because you see these particles hitting each other and forming new particles. So the two rays come together, right? The positron and the electron, they both hit each other and they annihilate each other and they create a photon. And the photon is represented by the gamma symbol in Greek, but the actual visual image that Feynman used in his diagrams is pretty much the ancient Egyptian DJ symbol, the J, right? Like Tahuti, Jehudi. The snake, the winding snake, the wavy snake, and the symbol in Egyptian, right? And that's the photon symbol. So the two rays, the forward ray and the backward ray of the electrons, are hitting the actual, the wavy pattern, and they become a photon. So it looks like all three of them are hitting at the same time, but they're not. What's happening is the negative electron and the positive electron, the positron, electrons are by nature negative. They're hitting each other and they're annihilating each other and they're becoming a photon, right? So that's what's happening in this picture. So the photon is then traveling, right, at the speed of light, right? And remember, electrons aren't traveling in a linear path. Electrons can, pop in and out of existence. Like I was saying, 10% of the electrons in our bodies can be anywhere in the universe. The other 90% are within our body, right? So, as far as, that type of stuff, that means that, quantum entanglement wise, we can be, a lot of different places. And that goes back to the ancestors. If you take everything on a fourth dimensional level, if you go to the car that's driving through New York City really fast and you see the trail of its light, that 4D light, if you take that car and you revert and you take go all the way back to where it was made at the factory, right? The whole worm-like trail of that car's existence, you're going to see where that car originated from. And you'd be able to see that, so in a fifth dimensional world, they'd be able to look at the fourth dimensional world like how we look at an apple or an orange as an actual object. So it's like your whole life being an actual object, right? And people from higher dimensions looking lower down, they can, they see the lower dimensions as objects, just like we see, Mickey Mouse's world, a 2D world. We see those as actual, just an object. Like, hey, I have a piece of paper that's shaped like a triangle, right? And that would just be a piece of paper object, right? But in Mickey Mouse's world, he's living in a flat world. That's his whole world is on a plane, right? So there's a book called Flatlanders you might want to check out. And I believe maybe Steve Segura actually showed us that in high school, Flatlanders, And so, with the Feynman diagrams, you'll see that the photon is traveling, right? It looks just exactly like the symbol in Egyptian, right? And also it's important to note, too, that although the Egyptian glyphs have been said to be, Rosetta Stone stuff is said to be deciphered and all that type of stuff, given that it was Germans that did all that stuff, we don't know if all those phonetics are actually correct, because there's no vowels in all these things. And a lot of these things were created from a Germanic perspective. And, so the people say the metanetter's been deciphered, but as far as how it's even said and things like that, we don't really necessarily know. A lot of people say, the first name of Egypt was Kuma, right? The way it was pronounced. But, there's so many different pronunciations, especially as far as the vowels. We don't know how long the vowels were or how, what they sounded like, if there were any, right? But, different, and over time, usually vowels, sounds can change. People create new accents all the time. Just like within our society, we've got languages evolving very, very quickly. Languages can evolve very, very quickly back in the day too. So just when you see the same glyphs, hieroglyphs, you don't know that, they were always spoken the same way in every dynasty, right? You can't assume that. You can never assume that. Just like we can't assume all these principles in physics apply to every universe in different multiverses, right? Another way of looking at it is like in Men in Black, when they go into the, they go into the actual, what do you call it? Locker in the bus station or the train station. Maybe it's like Grand Central Station. I'm actually in Men in Black 3 back in time in Warhol's party. I'm actually doing a cooking dance. Shout out to Bass God and shout out to Seb, what I'm saying, his DJ. But so as far as like time travel, different universes, all these things are all possible. There's it's infinite planes and things like that. And even if you take the strings of Laniakea, the name given to all the cluster of all the universes that we know so far, it looks like a like a giant lung, like a tree, and that's how we connect back to our ancestors in the fourth dimension. The fourth dimension, would just show the trail of your entire existence, which would look like a interweaving kind of worm, or like more of an interweaving pattern of knots, right? You're tying knots or loops, if you're going in a loop in life, or if you're going to new places. If somebody's traveling around the world and always going to new places, it's not going to be loops. Where if somebody's, just going to the corner, going back home, it's just going to be a loop of going to the corner back home. And another, you could see this in Donnie Darko, when out of his solar plexus, his future is kind of showing him where he's going in the future. He's seeing he's stepping outside of time and seeing his fourth dimensional trail, because to see your fourth, we can see our fourth dimensional trail when we wave our hands. But to see the entire existence of this universe as just an image is more like when you're traveling to higher dimensions, like, 7th, 8th, 9th, 10th. I think the 8th is locked. I think the 8th dimension is locked, like I was saying before. Every dimension is not the same. But yeah, as far as the Feynman diagrams, you can see that the photon keeps traveling, and then it splits into two Q symbols. I'm assuming these are quarks, right? And then a little gluon, a little G bounces off into a little circular spiral. So these diagrams, they are very, very similar to TTM as well. I was influenced by these because TTM is essentially the fourth dimensional trail of the Q point. So TTM mechanics and everybody that has a matrix poster, these are all fourth dimensional movements of the crossfader over time. I'm sorry, the Q point over time, and the clicks, the clicks represent the crossfader. Because trigonometry is the movement of waves, but calculus is when you start to cut those waves up. So what turntablists are doing is calculus, you know what I'm saying? And that works with all reality and existence in general. For those that don't know, about 21 years ago, I created something called the Turntablist Transcription methodology, which is a system of music notation for DJ music that's used all around the world.
They call it TTM.
Turntable transcription methodology. The graph represents sounds, right?
It's used in elementary schools in the UK. So I'm going to just go over basically on a deeper level what a photon can do. Even though, photons are represented by gamma, it's important to note that they're not gamma rays. You know what I'm saying? The gamma ray is a type of electromagnetic spectrum ray, but it's not all encompassing. It's just one spectrum. Gamma rays are just one spectrum. Our visual light spectrum is just a limited spectrum, right? Different insects, different animals can see much farther in different spectrums, but our spectrum is very much limited. To the whole kind of rainbow spectrum, right? And then there's infrared and ultraviolet below and above us, and then it gets to all these other types of waves and things like that. So even though they use the Greek gamma symbol for the photons are not only gamma rays. That's what I just wanted to make clear. All right. So now, if you think about particle wave duality, the fact that the Copenhagen experiments showed us that when a photon is shot through, it can act like a wave or it can act like a particle depending on if the person's looking at it or not. And that kind of goes to the tree falls in the forest kind of thing, and does it make a sound? And the Copenhagen experiment shows us it's different. It doesn't necessarily make a sound if you're not there experiencing it. And you know what I'm saying? Like, obviously things are happening, but they call them quiff pops and quiff, the seeing the experience actually affects the experience. So there's no such thing as an objective experience, because when you're actually viewing something, it's actually affecting that thing that you're viewing. You know what I'm saying? And also look up the Book of Optics. You know what I'm saying? By Al-Hazan, the Book of Optics. Because the Book of Optics, that's the first book that we know about optics. You know what I'm saying? And this was written by a black man. over 1,000 years ago, I believe. And, they've tried to whitewash him over the years, but look for the etching drawings of him. The crosshatch ones are the oldest. You know what I'm saying? If you're looking at it in the art history level, usually a lot of times the crosshatches are a lot of the oldest. You know what I'm saying? Because it's like, I grew up with all these fake history books showing just like a bunch of stuff drawn in the 1950s and 40s, 60s, different types of drawings. But you gotta really research. So, look up for Al Hazan. Yeah. So the Book of Optics, and I feel like that was his Greek name. I forget what his full Muslim name was, but I'll show the screenshot of all these things that I'm talking about. But yeah, the Book of Optics, because before that, a lot of the people living, coming from the Dark Ages, they thought that photons were shooting out of our eyes and scanning things, and he was one of the first to really put it down in modern book format, in Arabic, what I'm saying, that the photons and the light and the things are coming into our eye. You know what I'm saying? So definitely look up the Book of Optics. Yeah, so with the Feynman diagrams, I'm just going to read a little bit from Wikipedia. So the photon is a type of elementary particle that serves as the quantum of the electromagnetic field, including electromagnetic radiation such as light and radio waves, and the force carrier for the electromagnetic force. Photons are massless, so they always move at the speed of light in a vacuum, right? And our bodies are made out of light, out of photons, but they're wrapped in magnetism, so they're, they become other particles and things like that. And that's what the Feynman diagrams can show us. Like when you're mixing chemicals up, these different chemicals are being mixed up together, and they're forming different new strands of molecules, and certain things are bonding, certain things are knocking each other out of a certain bond, and things can alter and change, and we call that chemistry, right? So to continue that, the photon belongs to the class of bosons. Like all elementary particles, photons are currently best explained by quantum mechanics and exhibit wave-particle duality. Their behavior, and that's what I was talking about, the Copenhagen Experiment, because as far as particle wave duality, when they shot those photons through the double slit, sometimes they were acting like it was a wave going through the two double slits, and sometimes they act like there was like a shotgun blast and there's a bunch of little particles going through the double split. All right. So their behavior featuring properties of both waves and particles, right? So if we're made out of that, if we're made out of photons encapsulated in magnetism, different types of magnetism, then that that goes with that as well. You know what I'm saying? Because you can bump down using energy. You can bump down different molecules or different particles to different states. And people that do know about what's happening in Europe over the years with the supercollider that's in Europe, I believe it's in Switzerland. And shout out to More Mother. Shout out to More Mother. She just won the award to be able to do her music and do her practice at the Super Collider. But I do agree with Brett Carr that More Mother needs to be careful because they've done a bunch of rituals down there at the Super Collider stuff. You can look at some of Brett Carr, Aka Ra, some of his videos, and he's got the actual ceremonies that they were actually doing at the Super Collider thing. But you can actually look that up. And actually, shout out to the actual group Super Collider. There's a group called Super Collider with Jamie Liddell. He's ill. You know what I'm saying? And the cat he did that Super Collider project with, those two albums are, two of my favorite albums of all time, probably, from like a singer. Because I don't listen to R&B, but when it's glitchy beats, I like it. Aaliyah too. I like Timberland beats. But yeah, so so we're going to read through the rest of this. The modern photon concept originated during the first 2 decades of the 20th century with the work of Albert Einstein, who built upon the research of Max Planck. Now, actually, obviously, we know, we're talking about, rays and snake waves and stuff like that. These diagrams, all relate to or higher technology that was, we still can't replicate pyramids and things like that. So I'm not going to even read into all of those as far as the people that discovered all these principles, because, a lot of these things were unlocked when they raided Egypt in the 1800s and stuff like that. They unlocked a lot of different secrets, and we don't know which ones were locked and which ones were invented. But I'll give credit where credit's due so far. So Einstein introduced the idea that light itself is made of discrete units of energy. In 1926, Gilbert and Lewis popularized the term photon for these energy units. Subsequently, many of the experiments validated Einstein's approach. In the standard model of particle physics, photons and other elementary particles are described as necessary consequences of physical laws having a certain symmetry at every point in space-time. The intrinsic properties of particles such as charge, mass, spin are determined by this gauge symmetry. The photon concept has led to momentous advances in experimental and theoretical physics, including lasers, Bose-Einstein condensation, quantum field theory, and the probabilistic interpretation of quantum mechanics. It has been applied to photochemistry, high-resolution microscopy. See, with photochemistry, the colors that are emanating from our body, you can see the elements, every element, every flame, if you burn, in the periodic table of elements, if you burn each different element, every element is going to create a different color flame. Like we know if you burn copper, like my wedding ring right here, this is my wedding ring. It's got copper in the lining, you know what I'm saying? And if you burn copper, it's going to create a green flame. Let's see if I can change the hat. Oh, there we go. It's going to create a green flame, and every other element. So I'll show the flames too of the elements. You know what I'm saying? Look all that stuff up. That's real. They never taught me that in school. They never taught me that every single element has a different color. Like, why don't they have that chart in school? So I'm going to be compiling a bunch of things for my own pedagogies for teaching all ages and all levels of students, because we've come out of the dark ages. We're still coming out of the dark ages. And I think a lot of the things that that the dark ages are a part of is fracturing information and scattering it around, not putting it in one place so that people can capitalize off of it and get you a bunch of student loan debt. You know what I'm saying? Student loan debt to me is like slavery. In the future, there's not going to be student loan debt. It's like, why you're charging people for education, hoarding information. You know what I'm saying? Obviously, people should have private information, but like what they did at the beach that summer, that could be private information, their pictures. But if it's like, calculus and physics, why does it cost them money from all, why is it only making, the top cast, all the money, So, back to Feynman, the way this relates to the New Life stuff is that, New Life was talking about the fifth dimension, but he wasn't giving any idea about what the fifth dimension is.
We cannot perceive dimensions that are higher than the fourth dimension because they exist on a subatomic level. These higher dimensions actually deal with the possibilities. If a person were living in a world of 5 dimensions, then he would be able to play with time in different ways. He could move either in past or in future. It would also be possible for him to be present at different locations at the same time. When we see a rope from large distance, we only observe its one dimension, that is the length. But any insect moving on that rope will also see other dimensions of the rope, like its thickness. It will also observe the fine grooves and roughness and circumference of the rope that could not be seen by a distant observer.
You know what I'm saying? And that's why I'm bringing up these Feynman charts, and because as we've said before, you could look at the lecture with Asir. We spoke about Asir the Ducateers. We were speaking about dimensionality as well towards the end of the lecture. And you can look at it as a box within a box within a box within a box, kind of like the Russian those Russian toys. You know what I'm saying? Where it's a little person inside of a little person inside of a little person. And so you can think of multiverses in that way. People have depicted multiverses in a lot of different ways. So multiverses can be a box within a box, right? Because some of the higher dimensions are actually smaller dimensions. Even though it's outside of our dimension, you can look at, there's smaller dimensions and there's bigger dimensions, like what's happening in this animation where you're zooming out and somebody's able to look at something as like an object, you know what I'm saying? And that's what goes back to, being on the event horizon, because definitely check out the movie Event Horizon, because, in Event Horizon, they get near it, and, similar stuff that happens in Interstellar. Definitely check out Interstellar. They deal with kind of like what a fifth dimensional civilization is, a fifth dimensional civilization being one that can, looks at the history as an object, and they can change history, but they have their own history because their history is in their own fifth dimension, and it's just relative, because the people that are higher up in the sixth dimension above them look at their dimension as an object. You know what I'm saying? So, a lot of people say when people pass away, they see their whole life flash before them, but who's to say that they're not just going to the fifth dimension and seeing the fourth dimension as an object? So they're just looking at their whole life as like we look at an apple or an orange, and you're moving it around, looking at the different ridges or the different parts of it. It's just like, moving your life around and seeing, all the different things that happen, right? Because if you look back on a fourth dimensional trail, everything, you're going to see, all the trails, like you move from one city to another city, shout out to Tahir Hempful, like I was saying before, in his hip hop database project, where he's breaking down the rap lyric databases, and actually he was tracking Kanye's movements through his fourth dimensional trail. He was actually, because Google Trails, that's basically like your fourth dimensional movement. So if you, think about that, like your movement over time, your ancestors' movement over time, that's a trail. So a fifth dimensional view is going to be more of a view that's looking at that, all those trails like a map. And that's what the Feynman diagrams are. The Feynman diagrams are looking at all these particle interactions as a map, right? So, all right. So, yeah, and I'll put all those diagrams up, and that pretty much wraps everything up.